Welcome back to Prestressed Concrete Structures. This is the fifth lecture of Module 3 on Analysis of Members. In this lecture, we shall study the analysis of members under flexure, specifically the analysis for ultimate strength of flange sections. Analysis of flange section. A beam can have flanges for flexural efficiency. There can be several types of flange section. First, a precast or cast in place flange section with flanges either at top or bottom or at both top and bottom. Second, a composite flange section is made up of precast web and cast in place slab. Let us now see a few examples of this type of flange sections. In the top, we see precast T and double T sections, which are frequently used as bridge girders. Sometimes even they are used for making floors. In the lower part, we see a single box section and a double box section. These are also used as bridge girders. This type of sections can either be precast or it can be cast in place, but more and more precast sections are being produced and they are getting more popular. In this figure, we are seeing some other types of flange section where there can be flanges at the bottom to rest other members spanning on it. That means these members act as some primary beams carrying some other secondary beams. It can be an L section with the flange only on one side. It can be an inverted T section with flanges on both the sides. There can be I girders, which are very common again in bridge construction. In this sketch, we are seeing some composite sections. The web is precast and then moved to the side. The flange is cast in place made at the side. This type of composite sections are common in buildings or in bridges. There has to be proper shear connectors between the web and the flange to treat the section as a composite section. There can be various innovative types of composite sections. Some of them we shall see in the module under composite sections. Now, in this module, we shall study simple flange sections with rectangular webs and rectangular flanges. The analysis of a flange section for ultimate strength is different from a rectangular section when the flange is in compression. This is the first thing we have to be aware of, that we treat the section as a flange section only when the flange is under compression. If the flange is under tension, then we did not have to consider the overhanging parts of the flange and we can treat it as similar to a rectangular section. The next consideration is that if the depth of the neutral axis from the edge under compression is greater than the depth of the flange, then the section is treated as a flange section. Let us try to understand this from a sketch. In this sketch, we see a flange section where the flange in the top is under compression and BF is denotes the breadth or the effective width of the flange, DF denotes the depth of the flange, and D denotes the depth of the CGS of the pre-stressing steel. BW is the breadth of the web. There can be two situations. The first one, that the depth of the neutral axis at ultimate, which is represented as XU, is greater than DF, and in this case we treat the section as a flange section. But if the depth of the neutral axis is lower than DF, then we can treat the section as a rectangular section with a width of BF. Now, in this particular lecture, we are studying the first case where XU is greater than DF. In the previous sketch, XU is the depth of neutral axis at ultimate, DF is the depth of the flange. Thus, a flange section is analyzed differently from a rectangular section when XU is greater than DF. If XU is less than DF, the section is analyzed as a rectangular section. The another important consideration is to calculate the breadth of the flange or the effective width of the flange. If it is an isolated beam with a small width of the flange, then the full width of the flange can be considered as the breadth of the flange. But if it is a part, if the flange is a part of a slab, then we have to calculate an effective width from the slab, where the assumption is that the compressive stress is uniform over the effective width. The effective width of the flange is determined from the span of the beam, the breadth of the web, and the depth of the flange as per clause 23.1.2 of IS 456-2000. Under this clause, there are several expressions for different types of sections, which tells us how to calculate the effective width of a flange. In fact, to calculate the effective width of a flange, it is a very complicated exercise because the flange width depends on the span, the loading condition, and the end conditions of the beam. But the expressions that are given in the code are simple in nature to be used in conventional design. These expressions are not repeated here because the students are expected to be familiar with these expressions in a course on reinforced concrete design. Next, we are moving on to the analysis of a flange section. In the following sketch, the beam cross section, the strain profile, the stress diagram, and the force couples at the ultimate state are shown. Now, these conditions are considered. First of all, we are considering that XU is greater than TF. This ensures that the analysis is for a flange section, which is different from that of a rectangular section. Second, we are considering that the depth of the flange is smaller than 3/7 of XU. This ensures that the compressive stress is constant at 0.447 FCK along the depth of the flange. Let's understand this from the sketch. In the sketch on the left hand side, we are seeing the cross section of a flange section. As I mentioned last time, that for a limit states design for the ultimate strength, the first thing we have to draw is the strain profile, because the ultimate state is defined as the instant when the strain in the concrete at the extreme edge becomes 0.0035. That means that is our starting point to define our ultimate state. Next, based on that strain in the extreme fiber, we draw a linearly varying strain profile based on the hypothesis that plane sections remain plane till the ultimate. Now, once we have drawn the strain profile, we can draw the stress profile based on the constitutive relationship of concrete, and for this prestressing tendon, we have to note that the strain of the prestressing tendon at ultimate, which is represented as epsilon Pu, is equal to the strain in concrete at the level of the CGS plus the constant strain difference, which is denoted as epsilon DEC, or which is termed as the strain in the prestressing steel at decompression of concrete. In our last lecture, we had seen how to calculate epsilon DEC, and the expression is different for a pre-tension beam and a post-tension beam. In an analysis, epsilon DEC is given from the value of the prestressing force. Now, once we know epsilon DEC and the strain in the concrete at the level of the CGS, we can calculate epsilon Pu, from which we can calculate the stress FPU from the design curve of the prestressing tendon. From the stress diagram, we are moving on to the force diagrams. Now, here is the difference with respect to a rectangular section. We are decomposing the force diagram into two components, one which exists in the outstanding part of the flanges and part of the prestressing steel, and the other which exists in the web and the rest of the prestressing steel. The compression which acts in the web is denoted as CUW, and the corresponding component of the tension is denoted as TUW. CUW acts at a distance of 0.42 XU from the top fiber. The resultant compression in the outstanding parts of the flanges is denoted as CUF, and it acts at a distance of 0.5 dF, that is half of the flange depth, and the corresponding component of the tension is denoted as TUF. The purpose of decomposing the forces into these two components helps us to analyze the flange section properly, where we have been able to identify the individual couples, and we are able to calculate the lever arms for each of those couples. In this previous sketch, the tensile force is thus decomposed into two components. The first component, TUW, balances the compressive force carried by the web, which is CUW. Thus, we have an equation TUW is equal to CUW, because they are under equilibrium. The second component, TUF, balances the compressive force carried by the outstanding flange, which is CUF. And here we have the second equation, which is TUF is equal to CUF. Next, we are writing the equations based on the principles of mechanics. Before that, we are writing the expressions of those resultant forces. CUW is calculated from the design stress strain curve of the concrete, and it is given as 0.36 FCK times XU times the width of the web, which is BW. Next, CUF is given as the constant stress over the flange, which is 0.447 FCK, times the width of the outstanding flanges, which is the total width minus the width of the web, that is BF minus BW, times the depth of the flange, which is DF. Next, the TUW is equal to a component of the total prestressing steel, APW, times FPU, and finally TUF is equal to the rest of the prestressing tendon, which is APF times FPU. And we can observe that each one of these couples are under equilibrium by themselves. Now, let us recollect that what are the three principles of mechanics we use in our analysis of sections. The first one is equilibrium of forces. Now, here we have two equations, one for the longitudinal force and the second is for the moment, that the internal moment is equal to the externally applied load. The second principle we use is the strain compatibility. Here again there are two components. One is that the strain in the level of the steel, the strain in the concrete is equal to the strain in the steel. And the second consideration is that plane sections remain plane and hence the strain profile is linear along the depth of the section. The third principle is the constitutive relationships, which relate the stress and strain in each of the material, concrete and steel. Now, let us see the equations based on these principles of mechanics. The first one is the equations of equilibrium, and here the first equation is related with the longitudinal forces. Sigma F is equal to 0. The total tension is equal to TUW plus TUF, which is equal to the total compression TUW plus CUF. And the TUW and TUF are expressed in terms of the area of the prestressing steel and the stress, which thus gives that Tu is equal to APW plus APF both times FPU, and that is equal to the CUW, which is 0.36 FCK XU BW, plus CUF, which is 0.447 FCK times BF minus BW times DF. Thus, this equation is the first equilibrium equation. The second equilibrium equation is sigma of the moment is equal to 0, from which we can find out the ultimate moment capacity or the moment of resistance, which is equal to the individual moments created by the two couples. The first component is equal to TUW times D minus 0.42 XU. D minus 0.42 XU represents the lever arm of the first couple, and the second part of the moment is given as TUF times the lever arm of the second couple, which is D minus 0.5 DF. Once we add them up and substitute the expressions of TUW and TUF, we get an expression of the ultimate moment capacity of the section, which is given as MUR is equal to APW times FPU times within bracket D minus 0.42 XU plus APF FPU times D minus 0.5 DF. This is the second equilibrium equation. Now, if we have to know the individual values of APF and APW, we can calculate them from the equations TUF is equal to CUF, and the procedure is that we calculate APF as TUF, which is equal to CUF divided by FPU. Now, CUF is given as 0.447 FCK times BF minus BW times DF. The whole divided by FPU is APF. Now, once we know APF, that means what we are doing is we know the stress in the outstanding flanges to be constant at a value of 0.447 FCK. From that, we are able to calculate the total compressive force in the outstanding flanges, which is CUF. Equating TUF to CUF, we are able to find out the part of the steel which balances the compression in the outstanding flanges. Now, given the total amount of steel, if we deduct this component APF, we get the amount APW. That's APW is equal to AP minus APF. The second principle gives us the equation of compatibility, and here we see that from the similarity of triangles, we can relate the strain in the extreme fiber, which is 0.0035, with the strain at the level of CGS, which is epsilon PU minus epsilon DEC. Now, the expression is written as, from the principle of similarity of triangles, that XU divided by the total distance D is equal to 0.0035 divided by the sum of the two strains, which is equal to 0.0035 plus epsilon PU minus epsilon DEC. This is the compatibility equation, which relates the strain in the pre-stressing tendon at ultimate, represented as epsilon PU, with the maximum strain in concrete, which is given as 0.0035. And finally, we are moving on to the constitutive relationships. For concrete, the constitutive relationship is considered in the expressions of CUW and CUF. This is based on the area under the design stress strain curve for concrete under compression. We had seen this design stress strain curve in the module of material properties, that from the characteristic curve we define a design stress strain curve with a maximum stress of 0.447 FCK, and the area under this design curve gives the value of CUW, and for CUF, since the stress is constant, we get the value of CUF, which is equal to the constant stress times the area over which the stresses act in the outstanding flange. For the pre-stressing steel, the constitutive relationship can be expressed in the form FPU is equal to a function of epsilon PU, where the function f of epsilon PU represents the design stress strain curve for the type of pre-stressing steel used. This curve also we have seen in the module of material properties, that we have the characteristic curve of the pre-stressing steel, from which we define our design stress strain curve, and this design stress strain curve relates the stress at ultimate with the strain at ultimate of the pre-stressing tendons. Now, in the analysis of a flange section, the following variables are given. We know the geometric properties of the flange section, that is, we know BF, the breadth of the flange, we know BW, the breadth of the web, we know DF, the depth of the flange, we know D, the depth of the centroid of the pre-stressing steel, which is the CGS. We also know AP, which is the area of the pre-stressing steel. We also know epsilon DEC, the strain in the prestressing steel at decompression of concrete, which is a function of the prestressing force applied. And we also know the material properties. FCK is the characteristic compressive strength of concrete, FPK is the characteristic strength of the prestressing steel. Now, what are the unknown quantities in our analysis? First of all, we do not know the individual components of the prestressing steel APF and APW. That is, APF, which is the part of AP that balances the compression in the outstanding flanges, and APW, the part of AP that balances compression in the web. These two components we do not know at the beginning of the analysis. We also do not know the ultimate moment capacity or the moment of resistance, which is denoted as MUR, and we do not know XU, the depth of the neutral axis at ultimate. We also do not know the strain in the prestressing steel at ultimate, which is epsilon PU, and we do not know the stress in the prestressing steel, which is FPU. Now, the objective of the analysis is to find out MUR, the ultimate moment capacity. That means, let us summarize that what is meant by the analysis of a flange section. That we are having some given variables, we know the geometric variables of the section, we know the material properties of the section, we know the amount of prestressing force which gives the value of epsilon DEC, but we do not know some of the variables which we need in our analysis. First of all, we do not know the individual components APF and APW. We do not know the depth of the neutral axis, the strain of the prestressing tendons and the stress, and finally, we do not know the ultimate moment of resistance. Now, the objective of the analysis is, given those variables, we are trying to find out the ultimate strength of the section, which is MUR. That means, the final quantity that we need to have is MUR. Now, this set of equations are simultaneous equations which we solve in a nice way to meet our objective of calculating the ultimate moment of resistance. Now, the steps of this method, which is called the strain compatibility method, are as follows. First, to check whether the section at all behaves as a flange section or not, we assume the depth of the neutral axis equal to the depth of the flange. This is the border case of the transition from a rectangular section to a flange section. Now, with XU is equal to DF, the calculations are similar to a rectangular section, which we had seen in our previous class. That means, from the assumption, we find out a compressive force in the flange, we get the strain in the prestressing steel from the compatibility relationship, from which we get the stress using the design stress strain curve. We calculate the tension in the prestressing tendon. Now, if the tension and the compression, if we compare them, and if we find that the tension, which is TU, is greater than CU, then we need to increase XU, because we need to have a larger depth of neutral axis to have more compression. And once we have a depth of neutral axis which is larger than the flange depth, then the section is treated as a flange section with the equations that we have seen before. If the tension comes out to be smaller than the compression, then the depth of neutral axis has to be reduced. That means, XU is within DF, and we can proceed with the procedure of rectangular section with the breadth of the flange equal to the breadth of the rectangular section. Now, once we have determined that whether the section behaves as a flanged section or not at ultimate, and if it behaves as a flanged section, then we move on to those next set of steps, and here we do an iteration to find out the strain and stress at the level of prestressing steel, and we have to satisfy the equilibrium equation of the longitudinal forces. In our next step in the analysis of a flange section, we assume FPU equal to the maximum allowed value as per the code, which is equal to 0.87 FPK. Now, once we have assumed FPU, we can calculate the individual components APF and APW from the previous equations, which we have written them again, that APF is equal to 0.447 FCK times BF minus BW times DF divided by FPU, and APW is equal to the total amount of steel AP minus APF. Thus, by assuming FPU, since we know all other quantities, we are able to calculate APF and APW. Next, we calculate the epsilon PU from the compatibility equation, equation 3E9, which we have rewritten in this form, that epsilon PU is equal to 0.0035 divided by XU by D minus 0.0035 plus epsilon DEC. Thus, once we have assumed XU, we can find out the strain in the prestressing steel. We calculate FPU from the constitutive relationship. FPU is equal to F of epsilon PU. Now, earlier we had used the FPU to calculate APF and APW, and now we have found out another FPU, and we check whether this FPU is same as the value assumed in step 4. If they are not same, then we update the value of FPU and repeat steps 5 to 7. Once we have converged that we have got a value of FPU which satisfies the compatibility, then with that FPU we are calculating APF and APW. Then we are able to calculate CUW, CUF, TUW and TUF. All these expressions for these individual forces were given before, and the quantities that we need are available with us. Now, once we calculate these individual force terms, we can group the tension force and compressive force and check the first equilibrium equation, which is Tu is equal to Cu. If this is satisfied, then our assumed Xu is correct. If this is not satisfied, then we need to iterate with a new value of Xu till the convergence is met. That means our solution steps are similar to a rectangular section. That means we start with an assumed depth of the neutral axis. We calculate the strain and the stresses in the prestressing steel using the compatibility condition and the constitutive relationships of the prestressing steel. We calculate the tension in the prestressing steel and the compression in concrete. Now, if these two are equal, then the first equilibrium equation is satisfied. If they are not equal, then the equilibrium equations are not satisfied, and we need to change the value of Xu. We change the value till we have Tu very close to Cu, and where we are satisfied with the convergence. Now, at this stage, we are able to calculate the ultimate moment of resistance, which is mu r, which is given by the expression which is equal to TUW times the lever arm d minus 0.42 XU plus TUF times the lever arm, which is d minus 0.5 DF. Once we have calculated mu r, this capacity can be compared with the demand under ultimate loads. That is the objective of analysis, that finally we are calculating the ultimate moment capacity, which we compare with the moment demand under the factored loads. Now, in the strain compatibility method, the difficult step is to calculate XU and FPU, because we have to go through a iterative process which satisfies the strain compatibility equation and the constitutive relationships and the equilibrium equations. Now, if we want to bypass this method, the code allows us a simpler method which is similar to the approximate analysis for a rectangular section. This analysis is done based on table 11 and table 12 of appendix B of IS 1343-1980. Last time I had mentioned that these tables are given with respect to a variable which is a measure of the total pre-stressing steel times its strength divided by the area of the concrete times the characteristic strength of concrete. This quantity is denoted as the reinforcement index omega. Now, when we use this table for a flange section, then the area of concrete that we have to take is equal to the breadth of the web times the effective depth of the CGS. And hence, since this is different from a rectangular section, we are denoting the reinforcement index with a different subscript, and here it is represented as omega with the subscript Pw. The omega Pw is given as APW times FPK divided by BW times D times FCK. And thus, the omega Pw uses a fraction of the pre-stressing steel, which is APW, and it also uses only the breadth of the web in the denominator. Now, we had seen that as the pre-stressing steel increases, omega Pw will increase and the value of XU will go up. That means, with increasing amount of steel, we need larger depth of the compression to balance the tension in the steel, and also with increasing omega, beyond a certain value the stress in the steel decreases. That means, a lower amount of stress in the steel will be able to equilibrate the compression in the concrete. Next, we have to be careful that when we are using this approximate analysis for a flange section, we need to calculate APW from the total pre-stressing steel. The calculation of APW is from equation 3E8, which is APW is equal to AP minus APF, but APF depends on FPU, which is unknown, and hence again an iterative procedure which is similar to that we have seen in the strain compatibility method is required. That means, we have to assume an FPU, calculate APF, from APF calculate APW, then calculate omega, from which we can calculate FPU, and we will check this final FPU with our assumption. If they are not close, then we are updating our assumption and making another cycle. Now, in all this analysis, we had assumed that the depth of the flange is less than 3/7 of XU. The purpose of the assumption was that this assumption makes the stress in the flange constant, and the calculation of the CUF was simple using the constant stress 0.447 FCK. But if the depth of the flange is larger than 3/7 XU, then the flange depth is basically larger than the depth of the constant compressive stress. In that case, the code allows us to define an equivalent depth of the flange. This equivalent depth means that the compressive force in the flange will be equal to the compressive force in this new flange with the equivalent depth, and the expression of this equivalent depth is YF equal to 0.15 XU plus 0.65 DF. Thus, the equivalent depth depends both on the depth of neutral axis XU and the depth of the flange, which is DF. The equivalent depth YF is substituted for DF in the expression of MUR. That means the only difference we have when the depth of flange is large is that we are using an equivalent depth instead of the actual depth of the flange in the expression of the ultimate moment of resistance. Otherwise, all of the steps are similar. Let us now understand this procedure of analysis for a flange section with this example. A bonded post-tensioned concrete beam has a flanged cross section as shown. First of all, what we are knowing is that this is a bonded post-tension beam. It is pre-stressed with tendons of area 1750 millimeter square and effective pre-stress of 1100 Newton per millimeter square. That means the area of the pre-stressing steel and the effective pre-stress are given. The tensile strength of the tendon is 1860 Newton per millimeter square. That means FPK is equal to 1860 Newton per millimeter square, and the grade of concrete is M60. That is FCK equal to 60 Newton per millimeter square. Estimate the ultimate flexural strength of the member by the approximate method of IS 1343-1980. In our last example for a rectangular section, we had solved by the strain compatibility method, and here we are solving by the approximate method as given by the IS 1343. The cross section of the section is as follows, that the flange width is 460, which is the effective width of the flange. The depth of the flange is 175. There is also a flange at the bottom, but we will not consider this flange in our analysis because this flange is under tension. The CGS is located at a distance of 115 from the soffit of the beam. The width of the web is 140 millimeters. The total depth of the member is 900 millimeters. First, we are calculating the effective depth, which is the total depth minus the distance of the CGS from the soffit. 900 minus 115 gives us 785 millimeters. Next, we are assuming the depth of the neutral axis equal to the depth of the flange to check whether the section will behave as a rectangular section or as a flange section. Now, once we assume XU is equal to DF equal to 175 millimeter, we can treat the section as a rectangular section. Now, for the rectangular section, omega P is defined as the total pre-stressing steel times FPK divided by the width of the flange times the depth times FCK. Substituting these values, we get omega P is equal to 0.15. Note that here B is equal to 460, which is the breadth of the flange, and AP is equal to 1750, which is the total amount of prestressing steel. Now, from table 11, corresponding to a value of omega equal to 0.15, we find FPU divided by 0.87 FPK equal to 1. That means the prestressing steel has a stress which is the maximum allowable value by the code, and that is equal to 0.87 times FPK equal to 0.87 times 1860 is equal to 1618 Newton per millimeter square. Now, once we know the stress in the tendon, we are able to find out the tension force, which is AP times FPU, which is equal to 1750 times 1618 is equal to 2831.5 kilonewtons. This is the tension in the tendon. The compression is calculated as 0.36 FCK times XU times the BF, and once we substitute these values, we get 1738.8 kilonewtons. Now, comparing these two values, we find that TU is much larger than CU, and hence we need to increase the XU beyond DF to have more compression in the concrete. Now, once we increase XU beyond DF, we have to treat this section as a flange section at ultimate. Now, from now onwards, we are treating the section as a flange section, and hence the expression of the reinforcement index will also be different. First, we are assuming FPU equal to 0.87 FPK, which is the maximum value, equal to 1618 Newton per millimeter square. Next, we are calculating APF, which is the amount of steel balancing the compression in the outstanding part of the flanges, which is equal to 0.447 FCK times BF minus BW times DF divided by FPU. Since we have assumed FPU, we can calculate APF, and substituting all the values, we get APF is equal to 934 millimeter square. From this, we can calculate APW, which is equal to the total amount of steel 1750 minus APF, which is equal to 934, which is finally it gives APW is equal to 816 millimeter square. The reinforcement index for the flange section, as I said, that the expression is now different, which is equal to APW times FPK divided by BWD FCK. Here we are substituting APW instead of AP, which we did earlier for a rectangular section. APW is equal to 816, FPK remains same, and again in the denominator we have BW instead of B, and BW is equal to 140, and D remains same, FCK remains same, and we are able to calculate omega PW, which is equal to 0.23. Again, going back to table 11, we find out that this time FPU is less than 0.87 FPK, and FPU by 0.87 FPK is equal to 0.92, from which we get FPU is equal to 0.92 times 0.87 times 1860 is equal to 1489 Newton per millimeter square. That means once we have increased XU, we also get a drop in the prestressing stress in the tendons. In our second iteration, we are picking up this calculated value of FPU as the value to calculate APF. With FPU is equal to 1489 Newton per millimeter square, we are recalculating APF by the previous expression, where we have substituted 1489 in the denominator, and we find APF equal to 1015 millimeter square. We are recalculating APW as 1750 minus 1015 equal to 735 millimeter square. From that, we are recalculating omega PW, which is equal to 735 times 1860 divided by 140 times 780 times 60, which gives omega Pw is equal to 0.21. Last time we had got a value of omega Pw equal to 0.23, and this time we are getting a value omega Pw is equal to 0.21. Thus, we can see that we are converging gradually. Now, with this new value of omega Pw, we are going back to table 11 and we are calculating Fpu by 0.87 Fpk, which is 0.94, from which we are recalculating Fpu as 1521 Newton per millimeter square. In our third iteration, if we substitute Fpu is equal to 1521 Newton per millimeter square, we calculate APF as 994 millimeter square, and we calculate APW as 756 millimeter square. We recalculate omega Pw, and which turns out to be same as the second iteration, which is 0.21. That means here we have converged to a value of omega Pw which is not changing substantially beyond the third iteration. Hence, this number of iterations are sufficient, and the values of Fpu that we have got, we can use that to calculate the ultimate moment of resistance. Thus, the values of Fpu, APF and APW have converged, and from that we are now calculating the ultimate moment of resistance, which is given as TUW times the lever arm d minus 0.42 XU plus TUF times the lever arm, which is d minus 0.5 times dF. Now, the first component of the moment is equal to APW times Fpu times d minus 0.42 XU. All these terms are now known to us, and once you substitute the values, we get the first component of the moment to be 739.9 kilonewton meters. The second component of the moment is given as APF times Fpu times d minus 0.5 dF, and once we substitute the values, we find out the second component to be 1054.5 kilonewton meters. Thus, adding these two up, we find out the total ultimate moment of resistance, which is equal to 1794 kilonewton meters. Today, we studied the analysis of members under flexure. Specifically, we studied the analysis of flange sections for the ultimate strength. We first saw the different types of flange sections that are possible in the construction. We treat a section as a flange section under two considerations. The first, that the flanges have to be in compression so that we get benefit out of the concrete under compression. If the flange is under tension, then we neglect the part of the concrete in the flange and treat it similar to a rectangular section. And the second consideration is that the depth of the neutral axis should be larger than the depth of the flange. If the depth of the neutral axis is smaller than the depth of the flange, then we can use the expressions of the rectangular section to find out the ultimate moment of resistance, where the breadth of the rectangular section is same as the breadth of the flange. In this lecture, we had considered a flange section which is constituted of rectangular web and a rectangular flange, and there we found that when XU is greater than DF, in the analysis we decompose the force couple into two components. In one couple, the compression in the web is balanced by a part of the tension in the tendons, and in the second couple, the compression in the outstanding flanges is balanced by the rest of the tension. Now, this type of decomposition helps us to identify the individual lever arms of the two couples. From those expressions of the individual lever arms, we got an analytical expression of the ultimate moment of resistance of a flange section. Now, in an analysis, we are using three principles of mechanics. First, the equilibrium of forces, which has two equations. Next, equations of compatibility, which relates the maximum strain in concrete with the strain in the prestressing steel. And third, we have the constitutive relationships of the concrete and the steel. Now, in the analysis, there is a set of variables which are given, and there are few variables which are unknown. There is a rational procedure which is called the strain compatibility method, by which we solve the simultaneous equations in a logical manner. First, we assume the depth of the neutral axis, then we find out the values of the forces in the compression and the tension. If they are equal, then our assumption is correct. If not, then we again change our assumption and do another cycle. Now, the steps of the strain compatibility method can be involved if the section is more complicated than what we had studied. This can be implemented in a computer program, where once the variables are input, the program itself will do this iteration process. Else, if we do not want to use the strain compatibility method, then we can use an approximate method proposed by the code, wherein we calculate the depth of the neutral axis and the stress in the prestressing tendon based on a quantity called the reinforcement index. Now, for our flange section, the calculation of reinforcement index is different from that of a rectangular section. Here we take the part of the tendon APW in the numerator, and we take BW in the denominator. Now, once we know the reinforcement index, from the tables we can calculate the depth of the neutral axis and the stress in the prestressing tendon. From this, we can calculate the ultimate moment of resistance of a flange section. Today, we solved a problem based on the approximate method. In our next class, we shall move on to the third type of section, the partially prestressed section. Thank you.